In section 2.1, we learned how to solve second-order linear homogeneous ODEs with constant coefficients. There was 3 different cases, and I gave you a handout for that. Today, the difference is our equations are going to be non-homogeneous, which means the right-hand side of this equation is now going to be something that's not 0. And if it's not 0, this is what we call the non-homogeneous term. Everyone is going to have a solution like this. And this capital Y here, sometimes we use Y with a subscript P, or sometimes we use capital Y. But this is the general solution where you've got a capital Y plus the C1, Y1, C2, Y2 that we're familiar with. We call this part the complementary solution. And the capital Y is called the particular solution. When you have a non-homogeneous ODE, it's a little bit tricky to find this part. It's a little bit tricky to find the particular solution, the capital Y. It's actually pretty easy still to find the complementary solution, because the complementary solution part for the non-homogeneous ODE is the general solution to the homogeneous ODE. So if you just pretend the non-homogeneous term goes away, then you get the corresponding homogeneous ODE. You solve that to get the complementary solution, and then what you're left with is you still have to figure out what this capital Y is, the particular solution, but at least you get the complementary part for free. Well, not for free, but you get it from, you get it relatively easy. So let me rewrite that. My general solution to the non-homogeneous ODE is that particular solution plus the complementary solution. We could say the general solution is a particular solution plus complementary, right? Well, if I were to set these two constants equal to 0, C1 equals C2 equals 0, then you can tell one part of the general solution, an allowable solution to this differential equation, has to be just the particular solution. So that's what I'm saying here. A times y, capital Y double prime plus B times y, capital Y prime plus C times capital Y has to be equal to G of T. That has to be true as an equation. And then since the complementary solution is a solution to the homogeneous ODE where the right-hand side is 0, you can kind of see how this works here. Because when you add all of this together, we see that it's okay to just go ahead and add the homogeneous solution onto your particular solution and get a solution to your non-homogeneous ODE. How do we find the capital Y part? How do we find the particular solution? The procedure is called variation of parameters. And it goes like this. You make sure that you have a second order linear ODE with constant coefficients and a non-homogeneous term. Then you imagine the ODE is homogeneous, right? So just imagine that the right-hand side is 0. And you solve for the homogeneous complementary solution, right? Like we talked about. We already know how to do that. Now, what we're going to do next is we are going to replace the C constants with U1 and U2 where those are no longer constants, but u1 and u2 are going to be a function of t. This is kind of like the reduction of order method, where I don't exactly know what this solution is going to look like, and this is giving me a starting place. Now, since u1 and u2 are allowed to be any function of t, like they could be the reciprocal, like u1 could be something other function times the reciprocal of y1, and it just cancels out the y1, and you get whatever function you want. So this is not so much an ansatz as it is like very, 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 very flexible. It's allowing for almost any function to be the solution here. But at least it gives us a place to start from. So we find y prime, and of course you have to use the derivative product rule here, where you have like u prime y plus u y prime to expand the y prime. And what I need to solve for is two unknown functions. See if you can follow my logic here. I'm trying to solve for u1 and u2. We've got two unknowns, but there's really only one equation that they have to obey, right? There's one ODE constraint. And so this is going to be kind of a loose argument here, right? I'm just kind of relying on your intuition. But you know, if you've got two unknown variables and two constraint equations, you can solve a system of two equations for two unknowns. But if you have one equation with two unknowns, you can't really solve that, right? It's not specified enough. You have too many degrees of freedom. So what we're allowed to do is we're allowed to create an additional restriction. That means in addition to my ODE, we can also just make up an equation, right? And that's going to constrain my system with two equations and allow me to solve for two unknowns. So this is something that we just make up ourselves. You could technically invent a different constraint if you want to, but this constraint is formulated for a specific purpose. Because if we require that u1 prime y1 plus u2 prime y2 is equal to 0, that cancels out some of these terms in the y prime expression. It'll cancel out that one and that one. So that way when I simplify y prime, I just get u1 y1 prime plus u2 y2 prime. So again, we're solving for two unknowns. We only have one equation we have to respect here, which gives us a degree of freedom. And what do we do with that degree of freedom? We choose to make up an extra restriction, and the extra restriction is nice because it allows us to simplify my expression for y prime. Then we want to find y double prime, because we're about to plug this into our ODE where there's a y prime and a y double prime. So we determine the y double prime. Again, we have to use the derivative product rule, but at least we're not turning 4 terms into 8 terms, right? Since I simplified a little bit, now I'm still, again, only turning these 2 terms into 4 terms. So it's better by a little bit. So now I've got this expression for y prime, and I've got this expression for y, and I've got this expression for y double prime, and we're going to plug these into my original ODE, and then we're going to simplify it. This is what simplifying it looks like. I'm rearranging everything according to whether or not the term contains u1 or u2 or u1 prime or u2 prime. And then the big cancellation here happens because y1 is a solution to the homogeneous ODE. And so that's all equal to 0. And y2 is also a solution to the homogeneous ODE. So that all goes to 0. And so after we are done simplifying my original ODE, we get this short little equation. We'll keep that for later. And this other one might look familiar because this is the extra one we made up. Right, that was here. u1 prime y1 plus u2 prime y2 equals 0. So now we have two linear equations with two unknowns. My two unknowns are u1 prime and u2 prime. At this point, remember, we've already solved for y1 and y2. So we also know what y1 prime and y2 prime are. And we get g of t and a. We get that from the original ODE we're trying to solve. So we've got two equations and two unknowns. And that means we can solve for u1 prime and u2 prime. We can use something like substitution to solve for that. Then, once we have explicit formulas, solved this equations or this system for u1 prime and u2 prime, you can take antiderivatives to get u1 and u2, and you plug that back into here, where we had assumed that my particular solution was going to look like u1 times y1 plus u2 times y2. Multiply those, that gives me a particular solution, and remember your general solution is going to be your complementary solution plus a particular solution. I've kind of been going back and forth between the notation, but right, this is the same thing as that capital Y we talked about earlier. Or in other words, like capital Y plus C1 Y1 plus C2 Y2. So that's a lot. I'm going to give you a piece of paper to summarize what you need to know about that. So you don't have to write every single thing by hand. Obviously, you can go to the website and you can pick up these notes too, if you want to reread that for any reason. But the handout I just gave you looks like this. Because you don't have to recreate all that work every single time. What I prefer to do, if I'm working through one of these problems, is I remember all the details about the complementary solution and how you add the complementary solution to the particular solution to get the general solution and what the u1 y1 plus u2 y2 thing looks like. But then the only extra thing you have to remember is this. You don't have to remember the full derivation for how this method works. You do have to memorize this system of equations. So in this system of equations, you only see u1 prime and u2 prime. You don't ever see u1 and u2 by themselves. That's easy to remember because after you solve for u1 prime and u2 prime, you still have to take antiderivatives. In the first equation, you get the y1s and the y2s. In the second equations, you get y1 prime and y2 prime. In the first equation, the right-hand side is 0. In the second equation, the right-hand side is g of t divided by a. So at some point, you got to memorize that. All right, I'm about to work an example. But do you guys have any questions so far before we do an example? No? Okay. Here's our first example. Solve the ODE and IVP. So step 1 says make sure this is a second order linear non-homogeneous ODE with constant coefficients. And yeah, checks out. Step number 2 says pretend it is homogeneous. And if this were homogeneous, my equation would look like y double prime plus y prime minus 2y equals 0. And then to solve, I would have to write the characteristic equation down. And I have to think about, do I want to factor this or do I want to use the quadratic equation? Sorry, the quadratic formula. How does this factor?
R plus 2, R minus 1.
Very good. So my solutions for R will be 2 real solutions and that means my complementary solution, which is the general solution to the homogeneous version, the complementary solution is going to be C1 times e to the t plus C2 e to the negative 2t. This is the complementary solution, and remember, my general solution to the overall non-homogeneous ODE is going to be the complementary solution plus a particular solution. So now our job is to find the particular solution. And the particular solution is going to look like u1 e to the t plus u2 e to the negative 2t. So how do we find the u1 and the u2? We have to write down that system of equations I said you have to memorize. You got to memorize the system of equations where there's u1 primes and u2 primes. And there's y1 prime and y2 prime in the second equation. I think in the first equation there was just y1 and y2. And in the first equation it's equal to 0. In the second equation it was equal to gt over a. Let me make sure I copied that down correctly. So we got to solve this orange system of equations, which is saying u1 prime e to the t plus u2 prime e to the negative 2t is equal to 0. And then u1 prime, what's the derivative of e to the t? E to the t. And plus u2 prime, what's the derivative of e to the negative 2t? The g of t is referring to what? Yeah, this is g of t. So that's 5t. What is a? Yeah, this is just 5t divided by 1. Since my leading coefficient is 1. All right, so look at this system of equations. And I actually think, you know, sometimes substitution is the only way to solve this system of equations, but I think it would actually be nice just to take the first equation minus the second equation and see what we get. Because then the first term cancels out. And the second term is this minus negative 2, so 2 negatives make a positive, and I get 3 u2 prime e to the negative 2t. That would be equal to negative 5t. Or in other words, u2 prime would be equal to negative 5/3 times t times e to the power positive 2t. So now we have u2 prime. We're eventually going to need to take that antiderivative, but maybe for now, let's take this first equation again, and we will replace u2 prime with negative 5/3 t e to the 2t and see what we get. I'm going to have, from the first equation, u1 prime e to the t plus, and keep in mind that I'm multiplying this u2 prime times e to the negative 2t. So that e to the negative 2t is going to cancel out the e to the positive 2t when I multiply. And this is just going to be plus negative 5/3 t. And that makes u1 prime equal to 5/3 t e to the negative t. But I don't just need u1 prime and u2 prime, I need u1 and u2. So I've got to take antiderivatives. And that means u1 is going to be the antiderivative of 5/3 t e to the negative t. I could just take the 5/3 out. And then t times e to the negative t is a nice little integration by parts. If you don't remember integration by parts, the formula goes u dv equals uv minus v du. And if you've got a polynomial times an exponential, the polynomial is the u and the exponential is the dv part. So now writing u1 using the integration by parts formula, we get uv, which is going to be negative t e to the negative t, because, sorry, I should work all the parts. So dv is going to be, makes v e to the negative, sorry. Since this is dv, v will be negative e to the negative t. And then du will be dt. So uv is that minus the antiderivative of v, two negatives make a positive, du. So the antiderivative of e to the negative t is negative e to the negative t. I'm going to factor out a minus sign. And so that the greatest common factor between these two terms is negative e to the negative t. And then what I get left inside the parentheses is t plus 1. Okay, now back over here where we've got u2 prime. u2 is going to be the antiderivative of negative 5/3 t e to the 2t, which once again is going to be integration by parts, where t is the u and e to the 2t dt is my dv. That makes v 1/2 e to the 2t, and du is going to be dt. So u times v minus antiderivative of v du the greatest common factor between these two terms is going to be e to the 2t, so let me factor out negative 5/3 e to the 2t. What I'm going to be left with is 1/2 t minus 1/4. Or I could factor out a half too, I guess. Up to you how you want to do that. You can even say negative 5/12 and make it 2t minus 1. Not important. So we just found u1 and u2.
Do you have to do a plus c for both of those?
That's a good question. We'll talk about it in a minute. We're going to go back here to where we said this is my complementary solution. And my particular solution is going to look like u1 e to the t plus u2 e to the negative 2t. And then my general solution, of course, is going to be what I get if I add the complementary plus the particular solution. So let's write the particular solution next, which is u1 y1 plus u2 y2. And u1 y1 is going to look like, and I forgot what y1 is. Y1 was just e to the t, where y2 was e to the negative 2t. Yeah. So what would it look like to multiply u1 times y1? Well, e to the negative t is going to cancel out e to the t, right? So that first term is just going to be negative 5/3 t plus 1. The second term, u2 times y2, well, u2 has e to the positive 2t. So when I multiply by e to the negative 2t, that's going to cancel. And this is going to be negative 5/6 times t minus a half. And I should collect like terms. Like the stuff multiplying t is negative 5/3 plus negative 5/6. Which is like negative 15/6. That would be like negative 5/2. We'll call it negative 5/2 t. And then the constants would be like negative 5/3 minus 5/12 which is like negative 20 twelfths, minus 5 over 12, which is like negative 25 over 12 or something like that. To be honest with you, this constant doesn't matter, and I'll explain. Well, actually, that does matter. Hold on. Does that constant matter? I think it does. Maybe I should pay more attention. First of all, I messed up. Two negatives make a positive, right? That's actually plus 5 over 12. Negative 20 twelfths plus 5 over 12ths makes negative 15 twelfths. And negative 15 twelfths is 5 over 4. Very good. So that's my particular solution, isn't it? And then the general solution is going to be the complementary solution plus the particular solution. So that the general solution is going to be C1 e to the t plus C2 e to the negative 2t minus 5 halves t minus 5 over 4. All right, now we're ready to answer Carter's question. Carter said, after I take these antiderivatives and I get the u1 and the u2, should I add a constant at the end? And maybe we should, because when you take an antiderivative, you can have a constant. That's everybody's, that's everybody's Ninth Amendment right. I don't know what the Ninth Amendment is. What's the Ninth Amendment? Nobody? Okay. I'm glad we're all ignorant of civics. But what would that look like now when I go to my particular solution, and my particular solution is supposed to look like this? I would have u1 times y1. Well, what if I had u1 plus a constant from antiderivatives times y1? And then I would have u2 plus my constant from taking the antiderivative times y2. Well, then my expanded out particular solution would look like that, wouldn't it? Where this is the particular solution, u1, y1 plus u2, y2, from here. And then when I added that little constant in from taking the antiderivatives, well, now I have an arbitrary constant times y1 plus an arbitrary constant times y2. But that's already part of my complementary solution. And so the answer is, it doesn't matter which way you want to think about it. You can think about the arbitrary constants as coming from these antiderivatives of u1 and u2, or you can think about the arbitrary constants as coming from the complementary solution. It doesn't matter how you want to think about it. They show up exactly the same way under either philosophy. Okay. So it's a great question. It's a really smart question, but the answer is it doesn't matter. Okay. Any other questions about this solution? It was really fast and easy to find the homogeneous solution in purple there. But even something as small as changing the right-hand side from 0 to 5t, it really adds a lot of complexity to solving the ODE, doesn't it? And then the IVP, right, the initial value problem, says we're going to give some initial value for my y variable when t is equal to 0 and some initial value to its derivative when t is equal to 0. So let's talk about how you'd handle that. That part doesn't change very much. For the initial value problem, we would have to take this general solution and then take the derivative. So we would have y prime equals c1e to the t plus negative 2 c2 e to the negative 2t minus 5 over 2. And then we're going to set this equal to m0 whenever t is equal to 0. And then we go back to my general solution green equation and we set that equal to y0 whenever t is equal to 0. And now we've got a system of two equations with two unknowns. And the unknowns I'm trying to solve for are c1 and c2. And so I could subtract the second equation from the first. And on the left side, we'll get m0 minus y0 equals negative 3c2. And the negative 5 halves plus 5 fourths would be negative 5 fourths. And that would allow me to solve for c2. Because that would be 5 fourths plus m0 minus y0 divided by a negative 3. So c2 is solved for. And if I want to solve for c1, I could add the first equation plus 2 times the second equation. And I would get m0 plus 2y0 equals 3c1. The c2s would cancel. And then negative 5 halves minus 5 halves would be just minus 5, I think. And then solving for c1 means add 5 to both sides and divide by 3. Nice. That right there, those formulas for c1 and c2, this is the specific solution to my IVP. You know, it's kind of confusing. The sources that I was referencing, and even whenever I was learning this class forever ago, 12 years ago, they'll use the term particular solution to mean the solution to an initial value problem where you pin down the constants with specific values. And then they'll also use the word particular solution in this sense as the part of a non-homogeneous ODE solution that respects the non-homogeneous term. And I don't like using the same word twice for two different things, but it happens a lot in math. I think maybe next time I teach the class, I'll call it a specific solution to the IVP, so I can say it's a particular solution to the non-homogeneous ODE. I won't have to reuse the word, but anyways, questions? I hope I'm not going to offend anybody when I say this, but I get the feeling whenever I do ODEs that it's not hard, it's just really, really long. Do you get the same gist? we are 45 minutes into class and we've solved one example. You know, that kind of feeling. And my only word of warning is like when you work one of these problems on a test, like try to be really careful not to miss any plus or minus signs and to add your fractions correctly and stuff, because it could be so easy to make a mistake. When I grade your tests, I'm going to try to award partial credit wherever possible. Like I'm going to look and see if you've been doing the right steps and trying your best, and I'll forgive any places where I see a minus sign or a plus sign when they're supposed to be the opposite. But try really hard not to make any mistakes, because even making a mistake, it could make the solution more difficult. Like it wouldn't just like mess up your final answer, but it actually could throw you into a place where now your antiderivative is impossible instead of being a super easy, fast one. Yeah, just got to be careful. Really long problems. Okay. I also want to say something about this before class is over. A function is an elementary function if you can build up your function using a finite number of the following operations: adding, subtracting, multiplying, dividing, composing, powers and roots, and exponential functions and logarithms and trig functions and inverse trig functions. All of that would be an elementary function. So like in our Calculus 1 class, we only ever deal with elementary functions. And elementary functions don't have to be that simple. You know, like this is still an elementary function. Heck, even if I do something crazy like make it arctangent of all of this, this is still elementary because I'm just composing and adding and multiplying functions that are exponential and trigonometric and powers and inverse trigs. But there are functions that you probably remember from Calculus 2 where you cannot express them in closed form as an elementary function. And you actually can write down power series for these things. And that's where the word finite is important, because a power series is just an infinite number of operations like adding and multiplying. But there's a lot of functions that can be represented by power series. There's a lot of good analytic functions that are not elementary. And here are a few examples. A special function is like a non-elementary function that pops up relatively often. So my point of showing you these is that if you were to ever see the antiderivative of sine t divided by t, don't expect to be able to take that antiderivative, right? Like you just leave it. You just don't touch it. You just say, yeah, that's a non-elementary function. We're not going to mess with it. What about the cosine of t divided by t? That's non-elementary. No smartest person in the world could ever invent an antiderivative in closed form, in elementary form, for any of these, right? Every one of us, I bet, could sit down and write a Maclaurin series for sine of t over t, right? Like we could write a power series expression for this, but it's just not an elementary function. And so there's some other ones like 1 over logarithm, you can't take an antiderivative of this, e to the t squared, you can't take an antiderivative of that. So just be aware, because with differential equations, a lot of the solutions to differential equations, in fact, probably the majority of the solutions to the majority of differential equations are non-elementary functions. And so I'll show you an example of what to do, what I want you to do if you run into this on a test or your homework or whatever. Okay, solve the ODE and IVP. So we've got another second order non-homogeneous, blah, blah, blah. What we do first is we pretend it's homogeneous. If it were homogeneous, this is what it would look like. And the characteristic equation would look like this. The solutions to my characteristic equation would be, I think we can factor this. r minus 1, r minus 1. So the complementary solution, which is also the general solution to the homogeneous version, would be c1 e to the t plus c2 t e to the t. Hopefully you remember that from our section 2.1 notes. So that's my complementary solution. The way that we go about with variation of parameters is we say my particular solution is going to look like u1 e to the t plus u2 t e to the t. And our job is to figure out what u1 and u2 are, and we can do that if we solve a system of equations that looks like u1 prime y1 plus u2 prime y2 equals 0, and then the second equation will be u1 prime y1 prime plus u2 prime y2 prime equals g of t divided by a, which is going to be e to the t divided by t times natural log of t. Of course, y1 is e to the t, y1 prime is e to the t, y2 is t e to the t, and y2 prime is going to be a derivative product rule. Like that. So that my system of equations becomes u1 prime e to the t plus u2 prime t e to the t. The second equation is going to be u1 prime e to the t plus u2 prime e to the t plus u2 prime t e to the t. And to solve this system of equations here in purple, I suggest we take the first equation and subtract the second equation. So first equation minus second equation is going to be, well, those cancel. Those cancel. It'll be, oh, sorry, that shouldn't be equal to 0. Now we're ready to subtract. This should be negative u2 prime e to the t equals e to the t over t natural log t. The e to the t's cancel, and I find that u2 prime is going to be equal to negative 1 over t natural log t.
Should the other side also be negative? After
you subtract? Oh, yeah. So, good catch. That's what I'm telling you guys. Long problems. It's easy to make a little mistake. Very easy. Okay. So now we've got to plug in that 1 over t natural log t into the, let's say, the first purple equation, because that's the easier one, it looks like to me. So we do a little substitution here and write u1 prime e to the t plus, and then imagine what it would look like to multiply u2 prime times t e to the t, because the t's would cancel, right? Numerator, denominator, t's cancel, and I'll be left with e to the t divided by natural log t. In this equation in blue, I could divide both sides of that blue equation by what? E to the t. Yep, e to the t is never 0, so I can divide by e to the t, and I don't have to worry about dividing by 0. And that makes u1 prime plus 1 over natural log t equals 0, which makes u1 prime equal to 1 divided by natural log t. Negative. Ooh, almost missed a minus. And now that we found u1 prime and u2 prime, it's our job to take antiderivatives. So you can actually find u1 and u2. And that means u1 is the antiderivative of 1 over natural log of t dt. Well, this is one of those non-elementary functions. We cannot take this antiderivative, and not just because we're dumb. Like, it's already been proven that this is impossible to write it in closed form. So a shorthand that some people use is like a lowercase li of t plus a constant. Or you don't need a constant, right? We talked about how that's a little bit unnecessary when we solve for the u's. But li stands for logarithmic integral, and so that's a common shorthand. Back over here, if I want u2, this is the antiderivative of 1 divided by t natural log t dt. I'm trying to think, can I use a u substitution here? Maybe u equals natural log t. Yeah, that would work, right? U substitution. Because the derivative of natural log is 1 over t. Maybe I should have used a different letter besides u, but I'm sure you can follow along. So this is now the antiderivative of 1 over u du. And that would be the natural log of say that again.
Wouldn't it be tu, because it's tl and a t at the bottom?
Oh, but this part. Yeah, I'll color code it so you can see it a little easier. I need to replace this dt with du. And when I do that, it actually grabs the 1 over t dt and changes it out for a du. Okay, now the antiderivative of 1 over u would be natural log of u. And the natural log of u is the natural log of the natural log of t. So we're almost there to find my particular solution. Because the particular solution is u1 times e to the t. So that's going to be the negative logarithmic integral of t times e to the t. Plus u2, which is the natural log of t, times t times e to the t. And if I want my general solution, I just have to take my particular solution and then add the complementary solution. Nice. It's pretty ugly. The initial value problem is not impossible, but it would be a little bit grody. Because here's my logarithmic integral function, right? This is a typo that I need to fix in a future day. But I really can't use an initial time of 0. Because at the time t equals 0, I'm dividing by 0 on the right-hand side. So that's not good. I can't have my ODE itself be undefined here. So that's a typo that I'm going to go back to my office and fix for next year, 2 years from now. Could I use an initial time t equals 1?
No.
Why not, Carter?
Because there's 2 natural logs inside of each other. So natural log of 1 is 0, and then it'd just be another natural log of 0.
Yeah.
It's not possible.
In fact, yeah, the natural log of 1 is 0. And so again, I'm dividing by 0 in my ODE. That's not a good sign. So I think this problem should be fixed so that the initial values happen at t equals 2. And that way, you know, whenever I find my solution and it's natural log of 2, that's actually something we can work with. Something that's defined. So we'll call it this for my initial value problem.
Wouldn't natural log of 2 be negative, though, which would make the second natural log impossible?
The natural log of 2 is like 0.69. I think it's positive.
It's positive.
And then yeah, we get over here to where we plug in the logarithmic integral of 2, and that's going to be 0. I think this is a pretty standard way to define the logarithmic integral function. And notice how the lower bound of my integral is 2. Because they want to avoid the same problems. You don't want to have natural log of 1 in the denominator, because then you're dividing by 0. And so you start with something to the right of that singularity. And so I think a standard way to describe this is 2 in the lower bound. And maybe I should be using a capital L. Maybe I should make this capital Li for logarithmic integral, since that's the standard way to write it. But anyways, let's say capital Li of 2 is 0. And that means whenever I want the initial value and I set t equal to 0, or sorry, t equals to 2, then this is 0 plus natural log of 2 times e to the 2. Plus c1 e to the 2 plus 2c2 e to the 2 And then, of course, you'd have to take the derivative. What's the derivative of the logarithmic integral? That would just be 1 divided by the natural log of t. Yeah. Fundamental theorem of calculus right here. So when you take the derivative, that's something you'll have to do. And this is going to be still nasty because it's the derivative product rule and everything. Oh, yeah. So maybe this is going to take too long to do in the last 12 minutes of class to try to work out that initial value problem. Again, not that it would be terribly difficult if you know your derivative chain rule and your derivative product rule, but just because it would take so freaking long. And I'll be more aware of that when I write test questions. But I'm always going to try to write your test so that you can finish within a reasonable amount of time. Exercise 2. Consider the path of a projectile launched into the air. The projectile is acted on by forces of gravity and air resistance. Let gravity be a constant 9.8 meters per second squared and assume the force of air resistance is proportional to the speed of the object moving and acting in the opposite direction of motion. Write the ODE modeling this scenario and find the solution to the initial value problem where y is the vertical height, y0 is the vertical position at time t equals 0, and v0 is the initial vertical component of velocity. All right, so let me propose a way that we model this scenario. We could say that the second derivative of vertical position is negative 9.8. Because I'm thinking to myself, if y is vertical position, y prime is the derivative of position with respect to time. So what's y prime?
Velocity.
Yeah, y prime is going to be the velocity in the vertical direction. It's going to be the vertical component of velocity. And then y double prime is going to be the vertical component of what? Acceleration. Gravity is a force that's proportional to the mass of an object, and since F equals ma, gravity near sea level on Earth is a constant acceleration. 9.8 meters per second squared is acceleration. And since this is going to be acting in such a way to accelerate our object down and reduce its vertical position, I think that the vertical component of acceleration should be negative 9.8. Now that takes care of gravity, but we want our projectile to be acted on by gravity and air resistance. And what I want for the air resistance is that it would apply a force on my object, so it will create an acceleration proportional to the speed of the object. So it should be proportional to my vertical component of velocity, right? Velocity is kind of like speed, so it should be proportional to y prime. I'm going to use the lowercase letter k so that it's proportional. And I don't know the mass of this object, and I also don't know what constant it should be proportional to for like the air resistance part. And so I think the k is just going to take care of both of those things for us, the mass and the viscosity and the density of the air. Anyways, that's also going to it's not necessarily always going to be working in the downward direction, but it's going to work in the opposite direction as the velocity. So if the velocity is increasing, or sorry, if the velocity is positive, so your projectile is going up in the air, velocity is positive, then this is going to have a negative effect on your acceleration. So it's going to be accelerating down when the velocity is up because air resistance is working in the opposite direction. And then when this changes sign and your velocity is down, the air resistance is going to be pushing up because two negatives make a positive, and it's going to increase the y double prime. I feel like that works. Do you guys feel like that works as a model? So then, we can, nope, what do I do? Did I put my pen in my pocket? Yeah, okay. We can rearrange this ODE. And we find out that this is a second order, linear, non-homogeneous ODE with constant coefficients. And so the first thing we would do is we would pretend it's homogeneous. And in the homogeneous version, the characteristic equation looks like this. So my solutions for R will be zero and negative k. And in the homogeneous version, my complementary solution is going to be C1 times e to the power 0t plus C2 times e to the power negative kt. E to the power 0t is just 1, so keep that in mind. The homogeneous part's the easy part. Now we get to deal with the non-homogeneous part. And the particular solution is going to be something like u1 e to the 0t, which is just 1, plus u2 e to the negative kt. And the way we find u1 and u2 is we set up a system of equations that looks like u1 prime y1 plus u2 prime y2 equals 0. And u1 prime y1 prime plus u2 prime y2 prime equals g of t divided by a. Well, g of t is just negative 9.8 and a is 1, so g of t divided by a is negative 9.8. Let me rewrite that system and actually plug in stuff like y1 is just the number 1, right? Y1 prime will be 0. U2 prime times y2. Y2 is e to the negative kt. So y2 prime will be negative k, e to the negative kt. And then my second equation is going to be u2 prime, oops, I put that negative k in the wrong spot. So I can solve the second equation for u2 prime pretty easily. Two negatives make a positive, and then I get something like 9.8 over k e to the kt. And the antiderivative is 9.8 over k squared e to the kt. Take that and plug it into my first equation. I take the u2 prime anyways and plug it into the first equation. You don't need the u2. And then the e to the kt cancels with the e to the negative kt, and I get 9.8 over k equals 0, which means that u1 prime is negative 9.8 over k, and that means u1 is equal to negative 9.8 over k times t. So I'm ready to write my general solution, because my general solution is just going to be my complementary solution plus my particular solution. And the particular solution is going to be u1 plus u2 times e to the negative kt. And the e to the negative kt here is going to cancel out the e to the positive kt, so that the last term is going to be plus 9.8 over k squared. All right, if you want to solve the initial value problem, you just got to take y prime. You got to take that derivative. You got to plug in t equals 0. And then at the end, you'll have a solution that will model the vertical trajectory, at least, of a projectile shot into the air with some initial height and some initial position. But introducing the air resistance makes this a slightly more interesting trajectory, because without air resistance, it makes a parabola, right? With air resistance, it's not going to be exactly a parabola. It's going to look slightly different.